Coba dengarkanlah sumpahku dari hati. Aku cinta kamu. Jangan dengar kata mereka yang tak ingin kita satu. Yakinkan aku milikmu. Aku milikmu. Jalinan cinta tulus suci, terpadu terikat erat. Jangan terpisah lagi, waktu kan menguji cinta kita berdua. Mungkinkah ku miliki cinta seperti ini lagi? Jangan biarkan aku kehilangan dirimu. Coba dengarkanlah sumpahku dari hati. Aku cinta kamu. Jangan dengar kata mereka yang tak ingin kita satu. Yakinkan aku milikmu. Aku milikmu. Aku milikmu. Aku milikmu. Padu lembaran foto hitam putih. Aku coba ingat lagi warna bajumu kala itu, kali pertama di hidupku. Manusia lain memelukku. Lembaran foto hitam putih. Aku coba ingat lagi wangi rumah di sore itu. Kue coklat, balon warna-warni, pesta hari ulang tahunku. Dimanapun kalian berada, ku kirimkan terima kasih untuk warna dalam hidupku dan banyak kenangan indah. putih. Nah, ku coba ingat warna demi warna di hidupku. Tak akan ku mengenal cinta bila bukan karena hati baikmu. Siapa yang bisa buatku begini? Gila, ini bahagia apa menderita? Langit lagi bagus-bagusnya, tapi bagiku biasa saja. Dia buatku terkesima, menyapamu tak berani menciummu. Apalagi mata, pundak, lutut, kaki, gemetarku berdiri. Kalau sampai ku miliki, tak mau ku tidur lagi. Alamat malah nanti kau pergi. Kalau ada 9 nyawa, mau samamu saja semuanya. Ini dada, isinya kamu semua. Alamak, inikah jatuh cinta? Apa kamu sayang? Apa hayalan cubir aku sekarang ya? Buat mabuk kepayang, seketika pingsan, mana nafas buatannya? Can I see you for a minute? Boleh aku visit? See you mom and dad, aku pamit. Kalau memang naga-naganya kau berkenan, ku berangkat sekarang. Menyapamu tak berani menciummu. Apalagi mata, pundak, lutut, kaki, gemetarku berdiri. Kalau sampai ku miliki, tak mau ku tidur lagi. Alamat malah nanti kau pergi. Bila nyawa, mau samamu saja semuanya. Alamatku jatuh cinta. Ini dada, isinya kamu semua. Penuh tanya di dada. Alamat inikah jatuh cinta? Minimal kau bilang bila kau tak sayang, biar ku tahan perasaan. Jadi berhenti kau menatap, karena ku tak kuat berharap. Kalau ada 9 nyawa, mau samamu saja semuanya. Coba buka, isinya kamu semua. Oh, gawat diriku jatuh cinta. Kamu pesona, kamu yang lain. Ini dada, isinya kamu semua. Alamak, inikah jatuh cinta? Gila, naga-naganya ku telah jatuh cinta. Alamak, inikah jatuh cinta? Tak seharusnya kita terpisah, tak semestinya kita bertengkar, karena diriku masih butuh kau. Nah, maafkanlah sikap
cek 1 2 3 cek 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 1 cek cek
tes 1 Yesus ngomong dulu. Tes 1 2.
Terlalu bodoh untuk diriku, beban berat jutaan rindu, apalagi menahan egoku. Maafkanlah sikapku,
Cek
lupakanlah salahku, lupakan kepadaku.
Aman sih.
Takkan ku biarkan kau menangis,
Berarti dia tinggal nge-next di sini.
biarkan kau terkikis, terluka perasaan
Yang link-linknya udah dihapus-hapusin.
oleh semua ucapanku. Maafkanlah semua sifat kasarku, bukan maksud untuk melukaimu. Aku hanyalah
Oh gitu.
orang yang penuh rasa cemburu.
Lihat ya lagi.
Bila kau tak di sampingku,
Lagi di roll ngobrol sama
bila kau tak di sampingku, bila kau tak di sampingku. Malam ini
cek 1 cek 1 cek
mengisi sepiku, lama terasa waktu bergulir, karena dirimu tak bersamaku. Oh Tuhan,
cek 1 cek 1
bersamaku di sini menjagaku selalu. Dengarlah doaku yang tak pernah meminta bahwa dia kembali bersama, walau hanya sesaat. Masih terasa hembus napasmu saat ku gundah, kau lipur
cek 1 cek
kini terasa semakin dalam rasa rinduku pada dirimu. Oh Tuhan, tolonglah bawa dia kembali bersamaku di sini menjagaku selalu. Dengarlah doaku yang tak pernah meminta bahwa dia kembali Semoga berbincang tak karuan tanpa beban, dan juga hayalan tentang masa depan. Ku tak ingin cepat berlalu, waktu yang ku punya denganmu. Kita berdansa dan tertawa gandeng tangan. Semoga bergema sampai selamanya. Dunia pasti ada akhirnya, bintang-bintang pun ada umurnya. Maka tenang saja kita di sini berdua, nikmati sementara yang ada. Bersandar padaku, taruh di bahuku, relakan semua, bebas semaumu. Percayalah ini sayang terlewatkan. Ku sampaikan dalam nyanyian, bergema sampai selamanya. Dunia pasti ada akhirnya, bintang-bintang pun ada umurnya. Maka tenang saja kita di sini berdua, nikmati sementara yang ada. Bintang-bintang pun ada umurnya. Maka tenang saja kita di sini berdua, nikmati sementara yang ada. Semoga bergema selamanya. Pernah berpikir untuk pergi dan terlintas tinggalkan kau sendiri. Sempat ingin sudahi sampai di sini, coba lari dari kenyataan, tapi ku tak bisa. Jauh, jauh darimu, ku tak bisa. Jauh, jauh darimu. Lalu mau apa lagi kalau kita sudah gak saling mengerti? Sampai kapan bertahan seperti ini? Dua hati bercampur emosi, tapi ku tak bisa. Jauh, jauh sadar aku dan kamu tercipta, nggak boleh terpisah dan tak bisa jauh, jauh darimu. Ku tak bisa jauh, jauh darimu. Ku tak Di mataku kau begitu indah, kau membuat diriku akan selalu memujamu. Di setiap langkahku, ku kan selalu memikirkan dirimu. Tak bisa ku bayangkan hidupku tanpa cintamu. Dan janganlah kau tinggalkan diriku, takkan mampu menghadapi semua. Hanya bersamamu ku akan bisa. Kau adalah darahku, kau adalah jantungku, kau adalah hidupku, lengkapi diriku. No sayangku, kau begitu sempurna, sempurna. Kau genggam tanganku saat diriku lemah dan terjatuh. Kau bisikan kata dan hapus semua sesalku. Dan janganlah kau tinggalkan diriku, takkan mampu menghadapi semua. Hanya bersamamu ku akan bisa. Kau adalah darahku, kau adalah jantungku, kau adalah hidupku, lengkapi diriku. No sayangku, kau begitu sempurna.
Selamat datang di Institut Teknologi PLN yang berlokasi di Jalan Lingkar Luar Barat, Duri Kosambi, Kecamatan Cengkareng, Kota Jakarta Barat. Kampus Institut Teknologi PLN terdiri dari 12 lantai dan 1 basement. Sesuai dengan prosedur keamanan dan keselamatan, kami akan menyampaikan safety briefing. Setiap lantai di kampus Institut Teknologi PLN dilengkapi dengan peralatan dan fasilitas seperti hidran, apar atau alat pemadam api ringan, smoke detector, sprinkle air, lift, dan tangga darurat.
Saat ini, Anda berada di ruangan pembangkit lantai 2 Institut Teknologi PLN. Untuk mengakses tangga turun, silakan keluar ruangan, lalu berjalan ke arah kanan. Tunjukkan perhatian Anda terhadap beberapa perangkat keselamatan yang berada di dekat Anda, serta pintu keluar terdekat yang terdapat di sisi kanan dan kiri belakang ruangan. Apabila terjadi gempa bumi, segera lari sambil melindungi kepala dengan menggunakan benda yang dapat melindungi kepala Anda. Berjalan melalui pintu yang terdapat di sisi kanan dan kiri belakang ruangan. Ikuti arahan petugas serta melihat rambu tanda exit dan segera berkumpul pada titik yang telah ditetapkan. Apabila terjadi kebakaran dan jika di dekat Anda terdapat alarm kebakaran, segera lari ke panel tersebut dan pecahkan panel hidran yang bertuliskan alarm kebakaran. Nyalakan alarm kebakaran, brik gelas alarm akan menyala dan memberikan peringatan adanya kebakaran. Ikuti arahan petugas serta melihat rambu tanda exit dan segera berkumpul pada titik yang telah ditetapkan. keluar dari gedung tanpa melalui tangga darurat karena tangga darurat diprioritaskan untuk pengunjung yang melakukan evakuasi pada lantai yang lebih atas. Hindari kepanikan karena situasi telah dikendalikan oleh petugas yang telah tersertifikasi ahli K3 spesialis penanggulangan kebakaran. Apabila pada saat evakuasi Anda melihat pengunjung yang mendapatkan perhatian khusus atau terjebak atau dalam keadaan tidak dapat melakukan evakuasi, segera hubungi petugas untuk dapat ditangani lebih lanjut agar jiwa tersebut dapat tertolong. Hubungi tim medis jika Anda merupakan orang yang perlu diberi pertolongan pasca terjadinya peristiwa evakuasi.
Perlu kami sampaikan bahwa hari ini tidak ada latihan keadaan darurat. Jadi, apabila ada tanda keadaan darurat yang berbunyi sirine, maka itu adalah kejadian yang sebenarnya. Jangan panik dan ikuti petunjuk yang kami sampaikan tadi. Demikian safety briefing yang menjelaskan prosedur keamanan dan keselamatan yang ada di Institut Teknologi PLN. Terima kasih dan selamat beraktivitas.
Have you ever imagined a world without energy? A world when we can't go to school, where nights are dark without lights, and where the future feels uncertain. Energy is life, and behind every light, every machine, and every innovation, there's a generation ready to lead. Institut Teknologi PLN or ITPLN was born from this vision. Established in 1998 under Yayasan Pendidikan dan Kesejahteraan PT PLN Persero, ITPLN is a leading technology-based university in Indonesia dedicated to developing future leaders in the field of energy, technology, and infrastructure. More than just a place to learn, ITPLN offers a direct link to the industry through exclusive partnerships and job placements opportunities. Our students are not only equipped with academic knowledge, but also prepared for the real demands of the professional world. Today, ITPLN proudly manages 4 faculties, 1 vocational school, and 1 postgraduate program, offering a total of 18 study programs with the support of experienced lecturers, professional laboratories, and real industry-based learning. Students are prepared to face future's global challenge. At ITPLN, we believe that knowledge alone is not enough. To truly shape future's leaders, strong characters is essential. That's why we uphold 5 core values that guide every student, lecturers, and graduate. Come and be part of this extraordinary journey. Join us at Institut Teknologi PLN, and together, let's light up the future of this nation.
Come and join us.
And join us.
And join us
And join us. Come and join us
at Institut Teknologi PLN.
at Institut Teknologi PLN.
Come and join us at Institut Teknologi PLN.
Assalamualaikum warahmatullahi wabarakatuh. A very good morning, everyone. I hope you are feeling excited and ready for an inspiring session. Distinguished Vice Rector for Academic Matters, Professor Susi Fatena, the Honorable Representative from PLN, the Honorable Dean and Vice Dean of Faculty of Electricity and Renewable Energy, our distinguished speaker, Dr. Suhail, respected lecturers, and amazing student of ITPLN. Welcome to the International Guest Lecture, Power System Energy Transition and Renewable Energy Integration. My name is Septianisa, and it's truly an honor for me to be your master of ceremony this morning. We are about to embark on a session filled with knowledge, global insights, and meaningful discussion. Institut Teknologi PLN continues to strengthen its commitment to advancing innovation in energy system and sustainable technologies. Today's event reflects to our dedication to global collaboration and knowledge exchange in the green and digital era. And today we prove once again that ITPLN is not only learning locally but thinks globally. Okay. Ladies and gentlemen, to officially begin this special occasion, please rise for our national anthem, Indonesia Raya, followed by March of ITPLN. To all participants, please rise.
Indonesia tanah airku, tanah tumpah darahku. Di sanalah aku berdiri, jadi pandu hidupku. Indonesia kebangsaanku, bangsa dan tanah airku. Marilah kita berseru, Indonesia bersatu. Hiduplah tanahku, hiduplah negeriku, bangsaku, rakyatku semuanya. Bangunlah jiwanya, bangunlah badannya, untuk Indonesia Raya.
Thank you. Okay, now to open this event officially, it is my great pleasure to invite the Vice Rector for Academic Matters, Professor Susi Fatena. To the Professor Susi, the stage is yours.
Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Distinguished Dr. Junet Shuhel Osveren from Dundee, respected colleagues, the Dean of Bu Burumi, and then also all the and all the Civitas Academica in the faculty and then also in Institute Teknologi PLN, and then dear students, good morning. It is my great honor and privilege to welcome our distinguished guest speaker, Dr. Junet Shuhel Osveren from Dundee in United Kingdom. Today's lecture addresses a topic of critical global importance with the title of Power System Energy Transition and Renewable Energy Integration. This theme not only technically complex, but also strategically vital for the future of the energy, our economies, and also our planet. The global energy sector is undergoing a structural transformation. Conventionally centralized generation is progressively being complemented and in many regions replaced by distributed renewable resources such as solar photovoltaics, wind power, hydro, and energy storage system. Managing this transition requires interdisciplinary expertise, system thinking, and strong analytical foundation in power system engineering. That's why I think it's not only for the student or faculty in electrical engineering background, but also this speaker for today also important for other faculty in Institute Teknologi PLN. In this context, we are truly fortunate to have Dr. Osveren with us today. Coming from UK, a country that has made significant strides in renewable energy deployment and grid innovation, I think he will valuable international experience and academic insight for this today's speech. His expertise in power system and energy transition will provide us with both theoretical perspective and practical implication relevant to current global challenge. For our students who are here today and also in online, this lecture is an opportunity to broaden your understanding beyond textbook. Energy transition is not a distant concept, but it is happening now, as we know that our institution we have the aim to be in maybe in 20 years from now we go to net zero emission, and then we go to replace our energy that based on the environment, based on our nature, but to the more changeable energy. These engineers, researchers, and policymakers in this room also, I hope, will directly involve in shaping the reliability, sustainability, and realization in future power system. And to our faculty, the decision offers a platform for intellectual exchange and potential collaboration in advancing research and innovation in renewable, integration, and smart grid technology. Dr. Osveren, we are deeply grateful for you to be here with us and then sharing the knowledge in the area, and we look forward to gaining insight from you in your experience and also in your knowledge. Ladies and gentlemen, I think we can please join me in welcoming Dr. Junet Shuhel Osveren. Assalamualaikum warahmatullahi wabarakatuh.
Thank you very much, Professor Susi, for the visionary and inspiring remarks. Your words truly set the tone for today's lecture. Ladies and gentlemen, the moment we've been waiting for has arrived. Before we begin the lecture, please welcome our moderator, Mrs. Hasna Satyadini STMT, the Lecturer of Power System Engineering Study Program. To Mrs. Hasna, the stage is yours.
Assalamualaikum warahmatullahi wabarakatuh. Good morning, ladies and gentlemen. I am Hasna Satyadini and I will be the moderator of this international guest lecture. Before we start our session, I would like to introduce our today's speaker, that is Dr. Suhail Uzvaran. Dr. Suhail is a power system expert from UK and also Turkey, and he holds a PhD in electrical engineering from Durham University. And his professional work spans from transmission planning, renewable integration, and generating public policy in power system field. And in our today lecture, will be divided into two sessions. Each will be having 45-minute period. For the first session, the topic is power system in the age of renewable dominance. Without further ado, I will welcome our speaker, Dr. Suhail, to the stage. Dr. Suhail, the time is yours.
Good morning, everybody. I'm very pleased and honored to be here and do this presentation. I'll briefly introduce myself. I've been teaching over 35 years, and my first student from Indonesia was in 1996, and it was PLN who funded the students. And since I've also taught many funded students from PLN who are now senior managers in PLN. So I've always had a relationship through students and projects we did with PLN before. I'm very happy to be able to visit Indonesia. This is my third time, and very honored to do this presentation. And thank you for all the nice introductions that was made for me. Now, the title of my presentation is Engineering the Transition and from Reliability to Survivability. And because just to quickly frame the rest of the presentation, we are going through a transition in electrical power systems, and the transition is very transformational, and it's got to be managed and optimized. In traditional power engineering, when I first started as a student and then as a teaching, reliability was the dominant concept. You had to design and plan your systems based on reliability matrix. But from reliability during the transition, we have to start thinking of survivability, and this is what I'm going to try and explain the logic and the philosophy behind that. The system is going towards a renewable energy domination, so there will be more and more renewable energy resources coming into the system, and that brings problems with itself which are not unsolvable, but they have got to be managed optimally. I didn't change that. So the new question that you'll be trying to answer during your careers is that your grid has got 2 seconds to respond to a major fault. Typically, response times with thermal or stability factor high systems, but we are going towards systems where the stability factor is reducing. So what happens when you've got 0.4 seconds to respond? And this is going to be more and more the case as you introduce more renewable energy into the system, which are inverter-based resources. So the inertia of present systems, thermal dominate is about 5 seconds. Right? On average, you can take it down to 2 seconds, but we are going towards a future where it will be 0.4 seconds. And in some systems, in mini-grids where there's solar and diesel, you are there already. Right? So this requires new thinking and new planning tools. So I'll try and explain all this, and I shall be asking the question, what you would do when you have 0.2 seconds at the end of the lecture, okay? Now, because this is targeted to students and young engineers, as well as more senior ones, but the world you are going to inherit, I'm going to talk about a bit about the world that you are going to inherit during your careers. And I'll start with global context and try and put it in the Indonesian context. Now, the most important problem you're going to have is the energy, water, and food trilemma. Now, these are all interrelated concepts. If we first look at the statistics, first, you will see that today the world population is about 8.5 billion and going up, but we still have 775 million people with no access to electricity today. Now, this is important because everybody, all the developing countries are trying to increase their access to electricity and increase their standards of living, which is going to put more pressure on the existing fossil fuel sources, which is limited and diminishing. Now, as developing countries try to increase their quality of life and industries, they are going to spend more and more energy. At the moment, it is fossil fuel dominated, so spending more and more of that. And that means there's going to be more and more carbon emission, and that is obviously affecting the climate, and we can see the effects of it. Now, to produce energy, we need water. Now, 90% of the energy systems use water, and we've got huge demand going to come with for water as well. There's huge pressure on water resources. Also, the third dimension we have is food. Now, presently, again, over 700 million people go to bed hungry. So that means we need to increase the food production as well. But food production needs water, and it needs energy. So you can see how all these things are interrelated. For energy, we need water. Water is also needed for food. And so in the future, planning should be all interrelated and considering all different factors. And I'll come and talk about these more later on. So let's see a bit more details on this. Now that was the three dimensions I mentioned is global. Now I'll try and put this more into the Indonesian context. Now, 97% is the electrification rate in Indonesia, based on the statistics that I get from the internet. I have no insider information, so this is all publicly available information. Okay. Now, so there's 3%, but that is also, so there's 3% people more, you need to electrify, but that can be also misleading, 97%, because a lot of the islands, although they have access to electricity, they don't have sustainable electricity supplies, because there is often black, especially in the outer islands. So the outer islands also need to be completely electrified and have more reliable and resilient and survivable networks. So the next is, although Indonesia has got bountiful hydroelectric potential, and 70% of the hydro potential remains to be tapped. So this is a big opportunity for Indonesia as to be able to exploit these hydrological resources. But of course, using this water, you have got the constraint of food production, right? So you need the water for food as well. So it's got to be utilized for dual purpose. Now, when you come to the food energy linkage, there are 44 million hectares of agricultural land. Biomass and bioenergy represent a bridging technology, but it's got its limit. Now, I'll explain what I mean by bridging technology. Bridging technologies are the technologies you would need to go from today to the future, where you're going to have renewable energy dominant systems. So, but because you've got a lot of coal-fired generation in the system, you can't retire it immediately. We'll go into details why you can't immediately retire them, but it's got to be phased out, and then renewable energy has to be phased in. And to be able to do this, you need some transition technologies to be able to connect or to move from today to the future. So that briefly explains the energy, water and power, food and energy linkage. Now, maybe just before I go on to the next one, I'll briefly talk about the engineering implications of each of these trilemma dimensions. Now, with the energy access gap, I think engineering implication will be that the survivability would be the standard, and not just keeping the lights on once, but keeping them on reliably after a frequency event. Now, for those who are studying power engineering, will know that frequency is our main quality indicator, and the system operations set about around setting the frequency between 47.5 and 51.5. So you have a narrow band to keep operating, and that is a really important metric for the quality of and the stability of the system. Frequency events will be events where you lose generation, a lot of generation, and or you lose a big load where the frequency will now increase because there's more generation than the load that is that can be consumed. Now, for the water power mixes, the engineering implication will be that the grid planning must account for multi-year hydro variability, and pump storage planning will convert variable hydro into controllable dispatchable power. So because the hydro and because of the increased climate change, you are going to have variable output from hydroelectric. You will have sometimes too much water in the hydro dams, sometimes you'll have not enough. So the variability can be managed by having pump storage or utility sized batteries. So, but again, Indonesia is fortunate because there are lots of geographical locations where you can build pumped hydro, and there are few projects going for that at the moment. As for the food energy linkage, the engineering implication will be that, again, as a transitional technology, you need biomass fired or fueled generators, and this will preserve the inertia in the system because they are steam turbine based or rotating mass based generators. So, but there is of course you can't just use land to produce biomass because you need it for production of the food as well. Now okay, we've gone through this before, but let's just look into the electric. Oh, I didn't go. I'm going forward here. I'm not going forward there. So this is what I'm talking about. Okay, so we did talk about the safe drinking water, and you know, that is the electricity, energy, water, and food dimension. Now, let's have a look at some statistics, which is going to be more related to what we are going to talk about. 380 joules is the primary energy wasted per year, and it is 2/3 of all we produce. And this is because the system is basically thermal, right? Thermal systems are not end-use efficient. You know, they are about 25 to 30% efficient. Okay, so if you use coal to generate electricity, your primary source, which is called the energy stored in coal, gets converted to electrical energy, about 30% of it at best. Usually on average it will be 20-25%. Okay, so this is the useful energy you're using, and this is why we need to also transit to new forms of generating energy, because the thermal energy conversion, because of the Carnot cycle, which I'll explain a bit later, is not very efficient. Okay, so scientists have been warning us about the 1.5 degrees centigrade limit. Now that they were saying that if we exceed this threshold, there will be major climatic events, major weather incidents, right? And we've been warned about this for the past at least 10-15 years. Right? But despite all the international efforts to come to an agreement on carbon emissions, it has not been achieved. So this year we've exceeded, 2024, we've breached this 1.5 degrees increase in average temperatures, which means that as a result we are going to see more and more extreme weather events. Another dimension that is going to influence our thinking is that the 6% increase in electricity demand for Indonesia. So this is the electricity growth experienced in 2024, which is twice the historical average. Now, it's not just population increase which is causing this. Of course, you know, Indonesia is a developing country and living standards are increasing, and the average consumption per head is going to increase. That's natural. But there's also structural change in the demand. The structural change in the demand is going to come through electrification of the transport. It's going to come through extreme weather events, heat waves, and extra demand on air conditioning. And it's also going to come from, the most importantly, data centers. Data centers are new actors, demand actors on the system, and they come with huge demands on load and concentrated basically in the industrial areas. So that's a new increased pressure on the system. So if we come to the next slide, we'll have a look at the future till 2050 and try and discuss what infrastructure must survive. The infrastructure built today will be operating in 2050, and the scale shift must accommodate its structural and not incremental. So we are going to start with 2024 baseline, which is 6% growth, and by 2030, from what I can gather from publicly available information, Indonesia is targeting 44% renewable energy. And so that is 2 times the baseline. In 2040, the capacity increase must be like 2.5 times the baseline, and there will be more and more IBR transition. IBR is inverter-based resources. Right? IBR is short for inverter-based resources, and that is because solar power and wind energy requires inverters to convert it to AC power and get connected and synchronized to the system. So they all need, most of the renewable energy resources will need inverters. So this is why I'm going to use this terminology IBR dominant or RE dominant, which is renewable energy dominant. And so the baseline figures that I'm talking about there, saying 2.5 times and 3 times and 3.5 times, is the required increase in base installed capacity, firm capacity. So at the moment, Indonesia is about 100 gigawatts installed, and by 2050, different people estimate different figures, right? So I've looked at different figures, estimates, and the estimates change between 300 gigawatts to 500 gigawatts. Okay. So whatever it is, it's going to be the lowest estimate for future is 3 times today's installed capacity. But it could be 5 times more, depending on how the development goes. So everything you do today has got to cater for such a large step increase in the future. Every decision about which plant to build or to retire or convert takes place within this trajectory, and no decision taken today is neutral because it will affect the future. Now, that is in terms of generation capacity. And for transmission investment, from what I can gather from publicly available information, Java Bali grid is adequate for current load, but and there are plans for inter-island high voltage DC links, submarine cables, which will need redesign for load flow redesign for eastern Indonesia. Now, grid architecture being planned now must carry at least 3.5 times the current electricity by 2050. And people who are studying today, you are trying to be engineers, will graduate as engineers, and you'll have to design such systems, which is 3.5 times the capacity of today. Okay, you'll see this in your lifetime. Now, inertia budget. Okay, this is going to be one of the main points that I want to talk about. Now, this is the inertia constant, H. For those who are familiar with the swing equation, will know that this is the constant which determines the frequency of the system, right? Now, at the moment for Java Bali, it's quite good. There's 5 to 6 seconds, and the unit for the inertia constant is 6 seconds. So Java Bali is at the moment doing well, and but the inertia constant can fall down to 1 to 2 seconds as we introduce more and more inverter-based resources, solar, basically solar and wind as well. Now, the survivability engineering that I'm thinking about, challenge exists. The challenge for surviving exists precisely because the demand horizon requires the coal to renewable phase out. So, because the system, Java Bali system is coal energy dominant, the inertia is high, right? And the inertia is high because it's got spinning inertia, which is represented by H, which is the inertia constant. Now, as you retire coal and you replace it with solar or wind, the inertia will go down, right? Because these new systems have got zero inertia, and so the average inertia will reduce. So you have, when you retire a coal plant, you have to replace it with something which will increase the inertia of the system. Okay, and there are ways of doing it. Okay, that's the first thing you should do. Phasing out should be sequenced with inertia introducing approaches, and also you have to generate new tools which will allow you to operate within narrower boundaries, inertia boundaries, okay? And that means fast-acting protection, fast-acting batteries, pumped hydro storage, grid-forming inverters. It means synchronous condensers, okay? We'll talk about all these in detail. But what you need to now imagine is that coal retirement is not just an economic problem or requirement to meet the emission standards and or requirement to meet introduce more renewable energy because you've got limited resource base. It is also because you have got to calculate it properly so that you don't lose the stability and the operating point by losing inertia. So you've got to introduce ways, either increase it or manage operating with low inertia systems. Now, okay, the last item here is the skills gap. Sorry, just something is going wrong with my slide here, so just give me a minute to sort it out. Right, okay. So the skills gap, skills gap, power engineers in the past used to be trained for synchronous fossil fuel dominated systems. For 2050, we need engineers fluent in power electronics, grid forming control, system stability analysis for high IBR systems. I'm running out of battery here, which didn't think about. Can we have a power connection? Okay, apologies about this, changing systems. Right, okay, so the skills gap. Now, yeah, as I was saying, you know, the engineers of the future need newer skills or improved skills on power electronics, grid forming control, system stability analysis for high inverter-based resources systems. Okay, so bit more details on the what I call the electro part and the thermal part, and this is electro part is the new renewable energy dominated systems. It is, what I mean by that is the conversion of primary energy to useful energy. With solar, wind, direct primary source to electricity conversion, the efficiency is, as you can see, very high. But with the thermal part, which is coal, gas, and oil fueled, the conversion efficiencies are very low, and this is because of physics, and there's nothing much we can do about it. Of course, there's one technology which can increase the efficiency. It is called combined heat and power. To be able to use the energy waste from this energy conversion, to use it for district heating or industrial heating, and there are Indonesia can do this as well, you know, because there's a lot of food manufacturing industries can use this heat for their industrial processes. Hotels, swimming pools, laundry, hospitals can benefit from combined heat and power, because where you need heat and hot water, you can use the excess power or the waste heat power from coal-fired and gas-fired generators to convert it into useful heat, and that will increase the system efficiency to 78%. Okay. So another rule I want to talk to you about is the rule of 70. Anybody heard of rule of 70? Right. Rule of 70, if there is a growing quantity, right, which say something grows by 2%, right, and you want to estimate the time it will take to double that quantity, you take the growth and 70 divided by the growth factor will give you the doubling time. So if something grows by 2%, it will double in 35 years time. So this is a really important rule of thumb that you should keep in your mind. You can find out how long it will take for the energy requirement for Indonesia to double if it keeps growing at 6%. Right? So here we go. There's an example. at 6% per year, Indonesia's demand growth, it will double every 11.7 years, say 12 years. Right? So in 12 years, the demand will double. So by the time you graduate and start working, first 10 years of your engineering career, the system will have doubled its requirement. Okay? So you can do these calculations to realize the enormity or the importance of what you're doing. For example, let's try and do population increase of Indonesia, right? So let's say the population increase is 1%, right, which is very low. Okay. I don't know what it actually is, but I'm just for easy calculation. Let's say it's 1%. So 70 divided by 1, Indonesia's population will go up from, say, it is 275 now, to 550 million in 70 years' time. Okay, in 70 years' time, you will double the population of Indonesia. So you have got to think, you know, you need the energy resources, food, water, education, economy, jobs. It's all integrated. And 70 years is not a very long time to start catering for that. Right? So this people say Einstein said this, but I'm not so sure whether Einstein said this or not. But people attribute this to him. They asked him, what was the greatest danger facing humanity? Right? And because he was anti-nuclear bomb, as you know, he didn't want nuclear bomb to happen. Everybody thought is going to say, oh, nuclear atom bomb, A-bombs is going to be the danger. He said the exponential factor, misunderstanding or not knowing enough about the exponential factor is the biggest danger the humanity faces. Right? So anyway, so that is, I thought I will introduce this concept so you can have this in your mind all the time, right? How things will increase in time. You can calculate inflation, say, I don't know what the inflation is in Indonesia today, say it is 10%, right? The price of everything will double in 7 years' time, right? Whatever it is. So you need to earn twice as much as you are earning now to just keep up with it, right? So in your salary negotiations, think about this. Anyway, so right, so let's go on. Right, the more focused on your careers. 3-year students entering work in, say, year 3 students entering work in 2006 will retire at 2060-65, and there will be 3 full demand doublings within your career, right? Year 4 students entering work at 2025 and who will retire, say, 2060, will have 8 times the increase. Every infrastructure decision you make must work at 8 times the current scale. This is really important, and the change that you have to go through your working careers. Okay. Now, as I said before, the climate change. If you look at the temperature records, 2024, warmest year in 175-year observational record. So the 1.5 degrees centigrade threshold breached for the first time. So what does that mean for us? That means that heat waves will drive the peak demand for cooling, and also, you know, the normal daily peak will also be increased by the peak cooling demand. The grids that you design and operate must survive highest ever load at highest ever temperatures. Right? And then another dimension that you will have is hydro variability. The rainfall patterns shifts and they threaten the hydro output. Geothermal and solar must compensate. So how you do the backup changes, right? Because the hydro is variable, and so you have to make up the difference, and the way you calculate these have to change, and you have to now include not just load demand forecast, but you have to include the meteorological forecast into your calculations, right? So that will be really important. Now there is one major weather cycle in this area, which is the El Nino cycle. You will all know this El Nino cycle and El Nina cycle. So it is a weather event, and there's a cold Nino, and there is, I think the hot one is called El Nino, and the cold one is called El Nina. And this is a meteorological event which has got a cycle between 2 and 7 years. So it repeats itself every 2 to 7 years. And the hot one means extremely hot weather, low rainfall, reduced storage at hydroelectric dams or plants, which means reduced output for food as well, right? So the agricultural output will also vary. And then the cold ones, which coincide with high rain, and the high rainfalls means the hydroelectric dams will be overflowing, and there will be major flood and landslide danger, which will affect your electrical networks. So you have to, and there is storms. High monsoon season means more electric lightning strikes, which will affect the network, and you'll have more outages. So each cycle has got different consequences, right? So the high temperature Nino is a generation output constrainer and demand maximizer. So the hot cycle constricts your output because of the hydro availability, and increases your demand. So reduces your output, increases your demand, so it's a big pressure. The cold one, the other one, which is more rain, will then increase the chances of damage to your infrastructure, landslides, flooding, and also overflowing of the hydroelectric dams. Right? So both cycles, the hot cycle and the cold cycle, has got implications for electrical power engineers. Right, so I think, of course, when it is hot, the transmission lines also derate, which means that the power they can carry is reduced, right? So, and transformers age faster because they are hot all the time. They're higher, their operating temperatures are high. So that affects their insulation, wiring insulation. They age earlier, or they break down earlier, have many faults. So we are coming to a stage where we are not just talking reliability, we are talking how the system will survive. And not just talk about it, but make a standard of it. So we have to think of new ways, new standards of designing our systems where the system survives. Okay, and I'll try and explain what the difference means between reliability, resilience, and survivability, right? So there are three important concepts. Okay, so we are going to go from reliability to resilience to survivability, right? And okay, so let's try and define what we mean by reliability, right? So you are all studying, if you are studying power engineering, you are studying N-1 contingencies, right? N-1 contingency means that if you lose one important part of your network, like a major generator or a major transformer or a major transmission line, your system should be able to operate normally. So you design your system so that the operation will not be affected. And what I mean by operation is that you have normal voltage levels and you have normal frequency levels. So lose one generator, the system will still keep its frequency, the system will still keep its voltage within limits. Right? And so that's reliable. So you can design n-1, and for some really, really critical systems, you can do n-2, which means you lose two major components of your system to be able to operate normally, right? No loss of power, no loss of operating standards. Now, resilience means, and people also design for this, if there is an extreme event, storm, flood, more than few losses of generation, how fast can you recover? Can you absorb the shock without a blackout? So, as different from reliability, reliability means everything works as normal if you lose something. Resilience means if you lose major loss of major components, means you can recover quickly. Okay, not continue to operate. You are going to lose some load. You are going to lose generation. Your frequency will go down, but you can recover quickly, right? So that is a resilient system. If you can recover, you can absorb the shock and not have a total blackout. All the system goes down. Okay, so that's a resilient system. A survivable system goes beyond n-1 and n-2. What you are trying to answer is, can the system survive the event and maintain frequency within safe limits throughout? Okay, so you have to have some of the system survive, not total blackout, not all of the system, and so that you have basis for full recovery. Okay. One small footnote there: Indonesia's outer islands are already in survivability territory. Heatwave peaks, monsoon disruptions, and diesel shortages combine, and they lead to frequent blackouts in such systems. So they are already in that state. Okay, so what can happen in Indonesia, right? Again, from publicly available information, when you look at it from outside, you can say, okay, so we've got major 4 events: heat wave plus peak load, simultaneous peak cooling demand, transmission derating because it's hot. You have to derate your transmission lines. Java Bali peaks could hit generation ceiling during extended heat waves. And then the second important stress scenario is El Nino drought, and hydro output falls between 30 to 40% in drought years. Sumatra and Kalimantan systems are the most exposed systems. Coal or diesel must fill this gap immediately so that the system keeps operating. Monsoon, lightning storms, transmission fault spike during storm seasons, basically because of the lightning strikes. High inverter-based resource systems have less fault ride-through because of their short circuit ratios. Rate of change of frequency relays trip earlier in such instances. And when they trip early, that means it can lead to cascading failures. And of course, Indonesia sits in ring of fire. Substation and cable damage from earthquakes will create sudden large change of power events, and this is the type of scenario which low inertia systems cannot cope, and that will frequency relays will trip, frequency protection will trip the generators, and it can lead to cascading outages. So what I must stress is that nothing I said here is new to power engineering, right? Nothing is new. It is the sequencing which is important, and the stress it puts, and maybe the new analytical tools that we need to do all live calculations online and integrate forecasting, weather forecasting. Okay. So resilience, oh no, I didn't go forward. Right. I think Indonesia is the pivotal case now, right? Because, and the reason for that is fourth most populous nation on earth, 700 plus separate electricity systems across the archipelago, and demand growth expected within engineering careers is 3 times, maybe 4 times. Renewable target set for 2030 by government commitments is 44%, and it's a very ambitious target. So it is ambitious because of all the challenges that I've mentioned before. 6% demand growth in 2024 is twice the historical average, and is expected to continue. And of course, we've got many thousands of islands, and it brings logistical problems more than any other nation on earth. So in this archipelago, this is why I'm saying it is unique, and it could be like a laboratory and showcase for rest of the archipelagic nations, and there are few of them. But you've got the resources and the skills to be able to find solutions for these. And so you could be the global leader in archipelagic power systems. Okay, so we can at the moment separate the architecture of the grids into 3, right? You've got the Java Bali, which is a strong network, right? It's very strongly interconnected. It's densely meshed, and it's got high inertia. So it's got the widest operating envelope. The key challenge here is managing the coal retirement or the phase out. Was it? Did I switch this off? Oh yeah, I switched this off. Right, okay. I've switched my remote control. Right, okay, so we've got strong, densely meshed, high inertia, widest envelope system, Java Bali. And the problem here is how do you sequence, how do you phase out the coal retirement? Now, coal retirement, there is a technical challenge, there's a financial challenge, and there is a political challenge, right? So I'll briefly mention the financial challenge and maybe the political challenge, but mostly as engineers we are concerned about the technical challenge. So if we can manage the technical challenge, then it is up to the policymakers and the politicians to find the finance and sequence it, right? But as engineers, we have to be honest brokers. We have to tell the truth and say, this is what happens under this scenario, and this is what happens under this scenario, and this is how we can manage it with these results, and we have another scenario of we can manage it with these results, and then you can offer the options and alternatives. But explain it very well so that they can actually understand the implications of the choices that they are going to make. So this is really important. I think communication skills will be also maybe add to the skills list of engineers should have, to be able to really explain it to non-technical people. Okay, so managing coal retirement. Okay, the challenge is, of course, financial, right? So because PLN has got power purchase agreements, which means the coal-fired plants have sold the next 20-25 years of output, and there's a contractual obligation to buy it. And of course, if you don't do it, you can get out. There is the penalty clause, and the penalty, depending on the size of the plant, changes between, from what I can read, is between $500,000 to $1.5 million. So the what government or PLN has to pay if you shut down a plant is changes between half a million to 1.5 billion pounds. And if you think that the Java-Bali system is 60% coal, it's a huge challenge to retire them financially. Technically, it is also a not good idea. Technically, retiring 60% coal is not a good idea as well, right? So, so it's not impossible to retire most of it, not all of it. Most of it you can retire, but it's got to be phased in and sequenced properly with high inertia replacing methodologies or technologies, right? And then you retire it. You introduce the inertia, retire it. Introduce inertia, retire it, right? So, and of course, introducing new sources and renewable energy also requires finance. Retiring requires finance, introducing new resources, new inertia requires finance as well. So that is a challenge for the decision makers, but on us as engineers, you have to prepare the alternatives. Okay. Transitional, the second type of network for Indonesia is transitional. Sumatra and Kalimantan are good examples of transitional networks, which means that it's coal, basically hydro and rising solar generation. It's a medium density growing industrial regions. Networks are partially meshed. There's moderate inertia. I think the inertia is about, 2 to 3 seconds. Key challenges, sequencing is what you need to do now. Whereas in Java and Bali you can do it in the future, but in sequences has to be done in these transitional networks because they are low inertia systems. And then of course you've got the outer islands, eastern islands, low density, isolated communities, diesel dominant, some solar. It's got radial topology, low inertia, and narrowest operating envelope. So they are facing, the engineers in these outer islands are facing the problems that we are talking for Java and Bali in the future now. So they have to cope with radial topology, low inertia, narrow operating envelopes. And here I am introducing a new concept, which is the inflection zone, which we'll come to later. Inflection zone is where the frequency falls very suddenly. As you lose inertia, increase the penetration of renewable energy. There is a slow decrease in stability, but after a point, it will just like a cliff edge, and then the frequency drops and is not possible to recover. Now, national planning for PLN, of course, must accommodate all three typologies simultaneously, each at a different stage of the transition, because they are all at different stages of this transition to renewable energy dominated systems. Now, small isolated systems face a stability challenge that large interconnected systems don't, because large interconnected systems can transfer power from other generators from other regions. So for example, a 500 megawatt generated trip on Java Bali system with an H constant of 5 seconds and 25 gigawatt peak causes change of power event of about 2%. Well, the same trip on a 1 gigawatt outer island system causes change of power event of 50%. So the same power loss has got a bigger impact on a smaller system than it has on a bigger system, right? So the island sees the swing equation. If you look at the swing equation, rate of change of frequency is proportional to delta P there. So the island will see 25 times the rate of change of frequency fall to Java Bali example, right? So the same amount of generation loss will cause bigger drop in outer islands than it will in Java Bali system. So low system strength is the total generation capacity of single unit trips are large percentage of the total, and of course they have high reactance to resistance ratio on distribution cables. Reactive compensation is scarce, fault level is low, protection system sees smaller fault currents, and voltage recovery after a fault is slower without synchronous plant. So islands are most susceptible because they have 1 or 2 diesel generators and a lot of so the rest is solar plant which has got no inertia. So you lose 1 generator, it's got a huge effect on the system. So low inertia system is 1 to 3 diesel units provide all the inertia of the system, which is the outer islands, 1 to 2 seconds. Adding solar replaces synchronous generation, reduces the H further. So if it is 2, it's going to go down to 1. If it is 1, it's going to go down to 0.5. Trip of 1 diesel catastrophic H reduction, and it is not gradual, and there is no governor headroom for the system to pick up the frequency. Now, because they have got no interconnection, they cannot borrow frequency support from neighboring islands. They cannot transfer emergency power during a contingency. And submarine cable interconnection is one of the solutions, but it's expensive. So PLN must design, PLN engineers must design each island as if they were an entire system, not connected to anything else, and increase the resilience and the survivability of that system.
Doctor, sorry, the time is only 45 minutes.
Fine, yep. So yeah, that's a good point to stop anyway. So yeah, we're now going to stop according to program. I am famous for overrunning my lectures. So I've got previous students here who can verify that I always go over. Right? Okay, so I'll take questions now.
Okay, we open the Q&A session. The audience are very welcome to ask any question or if you have something to be discussed to the Dr. Suhail. Okay.
Thank you for the first time to ask a question to Dr. Suhail. I want to ask about the skill gaps in electricity. Do you have at first to eliminate the gaps? But I think there are quite in electricity of engineering Indonesian is from PLN or from the alumni of engineering in campus. Yeah? Do you have to first to eliminate the gap? Thank you.
You mean the gap in the energy?
Yes.
Yeah. Well, I mean, you mean when you retire the power plant, how are you going to replace the inertia, right? Is that, did I understand correctly?
I think it's more about the employment employment gap, like the skill gap between the previous engineer used to work in CFPP and now they need to be able.
Okay, okay, fine. Okay, I'm good. Okay, so yeah, I was talking about the skills gap. That's right. Yeah, and okay, well, with the engineers who are already graduated, there is a like educational half-time. I don't know if you heard of the concept. This means how much of what you learn, 50% of what you learn will be out of date in how many years, right? So there are interesting research on this. And for engineering, they reckon is 5 to 7 years. So in 5 to 7 years of what we know today, we'll lose half of it will be out of date. And it is true not just for graduating students, for everybody, right? Because the fast pace of technology. So everything I know now will be half of it will be out of date in say 5 to 7 years time. Right? So that means two things. For students will have to learn how to learn. So you have to know, and I will come to this because I'm going to talk about what tools you have now and what tools you will have in the future, right? And what skills, more details on it towards the end. So you have to learn, not just you have to learn your fundamentals very well, right? Your mathematics, physics, related to electrical. You have to know them inside out really well, right? Not just memorize, but you really understand them. And you have to also learn how to learn, right? So without good mathematics, you can't learn. So your mathematics must be really good, right? Because new learning will involve mathematics. Right? And you have to have very good knowledge of programming skills, right? Not just a language, but the philosophy of programming, because programming languages change. So if you know good philosophy, good rationale behind it, and know one language well, you can always update yourself. And if you know physics well and mathematics well, then you can always learn the new approaches to the analysis. Because physics and mathematics is the only thing which will not change, right? How you do it, you will have tools to do it, you will have computers to do it, but computers can lie to you, you can make mistakes, so you have to know what you see at the output makes sense, right? And that comes with good knowledge of mathematics and physics, so that you can understand what AI tells you. Does AI give you rubbish or kind of ballpark? You have to know the answer, ballpark figure, right? So that they calculate the detail. Okay. So that's and for the existing engineers who are acting professional, it is continuous professional development. I think all engineers should go updating every few years, and it should be a requirement by their organization that they do this continuous professional development. And of course, it's the same pressure as on the academic staff as well. Academic staff must be always engaged in research and updating themselves. So we are living in times of very fast change, and we all have to adapt to it. So there is no crystal palaces where we can sit and look. We all have to go down the coal mine and work at it. Learn, change, think. I hope that answers your question.
Okay, thank you so much for the answer. I think we still have time for one more question. Okay, one more question from the audience. Maybe from our online guests are very welcome to ask any question. You can use chat. Or maybe I have a question for Dr. Suhail. Well, maintaining survivability and also enhancing renewable energy penetration are having a contradicting conflict. what should the utility do to achieve those target while also having a budget limitation, Doctor?
I didn't understand the question, so if you can repeat.
Okay, well, you see that having we need to maintain our survivability and resilience, but we also need to achieve our renewable energy goals, and both having a contradicting effect. And what should the utility done while also having a budget limitation?
Okay, right. So yeah, well, that's the second part of the lecture. Short answer. Yes, of course, you've got to sequence it, and it's not an impossible task. It's a big challenge, but it is not an impossible task. So it can be done, technically, it can be done. But whether it can be done financially and politically is a decision that Indonesia will have to make with all the different actors working together, right? And I'm going to come to that as well, because I think energy sovereignty, resource sovereignty, and data sovereignty should play a major part in the decisions that you are going to make in the next, okay? Indonesia is both very lucky and also in some ways in a difficult situation. So there is a lot of ground for hope, and there is a lot of grounds for being prepared for challenges. Right? So okay, so this is, I'm going to start getting into that now, and the technologies that are available will be available. Analytical tools that you have now and you can develop in the future. So hopefully second half of my presentation will try and put these things together. And for the students here, I'm going to share my slides, and I've also prepared a lecture note for your professors to distribute. And I'm happy to enter into discussions later on. You can, send me your questions, and I'll have, between my travels, I'll try and find time to answer them. Okay. So how do we get out of this, or how do we face the challenges, right? So that is what I'm going to come into next. Now, Indonesia has got a lot of natural resources. Very, very lucky, unique position to be in. Abundant solar energy, and this coming from like a place like Scotland, you can see the big difference in solar energy, right? But even in Scotland, solar energy is making huge inroads and being used more and more, right? In fact, UK has to spill renewable energy. Sometimes, it is more than the system demand often, so they have to stop the wind generators, turn them out of the wind. So they are getting more renewable energy than is required at the moment, right? So yeah, not so much solar, but solar is also playing an important part. 200, from what I can read from public available academic publications and other sources, 200 plus gigawatts resource is available to Indonesia, right? Now, if you think that the present capacity is 100, so twice the present capacity is available in terms of solar. As primary energy as well, equatorial, sun, rooftop, and utility scale implementations can happen, and if you totaled all of them up, people are saying, like the International Energy Agency and places like that are saying that 200 plus gigawatts is available. Wind, 60 plus gigawatts wind is available. This is both coastal and offshore, and the potential is strongest in eastern islands. Geothermal, 24, about 24. I've also read some estimates that it is 36 gigawatts, right? But I took the lower estimate because these estimates are sometimes based on companies, let's say, selling their technology. right? So they are always, so you've got to be careful about where you get your statistics from, okay? So I took the lower end, it's 24, but people are talking about 36, 39 gigawatts geothermal potential. And my country of origin, Turkey, has got a lot of geothermal in the system at the moment, so they are using a lot of geothermal as well. So technology there is mature, right? It's being used at the moment. Large hydro potential, again, you know, sources talk about 75 gigawatts, right? And biomass 32 gigawatts. Now, there's one word of caution here. Agricultural biomass should be only based on agricultural waste, right? Not planting things to use for biomass, but because that takes away water and land away from food production. So biomass, in my opinion, should only be allowed and based on agricultural waste, palm residue, and the advantage of it. 32 gigawatt is a good capacity addition. Geothermal and biomass introduce inertia to the system, so they are one-to-one replacement with coal. So as you retire coal, you can introduce this, and the system doesn't lose its inertia. So there are good technologies, and there are good bridging technologies to use until that will give you an operating window of 40, 50 years where you can develop inverter-based resources even more. The technology will improve, battery technologies in 30, 40 years, it will be huge developments in those areas. But biomass and geothermal will give you the time to develop it, and it is also really important for energy sovereignty point of view, because these are local resources, and they are also technologies which are not, you know, like space age technology. This can be done domestically. You can produce everything required here domestically. So, and that will give you another operating window of 40, 50 years. So I think, personally, these are two really important resources, include also the hydro. So in between the hydro and you know, geothermal and biomass, you have got about 130, 140 gigawatts of capacity potential, which is more than today's, right? Okay, so lastly, I think another important contribution is waste to energy, right? Because as Indonesia develops, it gets more urbanized, there is increasing amount of waste in the system. So you can use this waste to convert it into energy. Now, I haven't come across any figures which gives me the potential gigawatt capacity for this, but that could be one of your graduating projects, final year projects. You can look into what potential there is in Jakarta, for example, to generate waste to heat, and these are important, and it's a mature technology. There are many people who operate this now. Okay, right. So I've talked about this, so I'll start getting into each technology itself and what the plus and the minus side of each technology. And then we will go into explaining what kind of technologies are available now to increase the inertia of the system. Okay, and then if you have time, I'll go into the tools available to you at the moment and what should be in the future. Okay, so let's proceed quickly. Okay, so what we have now is coal turbines, right? And we want to replace them with like solar PV inverters. Okay, so coal turbines, they spin about 3,000 RPMs. It stores kinetic energy in rotating mass, and inertia constant is about 4 to 6 seconds. Okay, between 4 and 6 seconds. So good. So this is our system, because if there is a loss of energy, the rotor keeps rotating because it's got kinetic energy in it, right? And it will keep rotating even if you didn't give any input to it. Shut down the fuel input. It will keep rotating 4 to 6 seconds. So it will keep the frequency going, okay? But of course, you are not going to shut down the input. So it can, what it means that for 5 to 6 seconds, it can absorb loss of energy, loss of generation energy. If another generator comes down, it can replace its kinetic energy for 4 to 6 seconds, okay? So it's an energy buffer against faults, and this doesn't need any automatic regulation. You know, it just happens in the system. And then after that, the governors of the steam turbine will come, and they will increase the energy input, so it will keep going at 3000 RPM, right? What I'm saying is that it will not lose the spinning 3000 RPM within the first 4 to 6 seconds. It will keep turning, right? And then you have to then, of course, to keep going, you've got to, the governors will act, they'll open the inputs, and there'll be more fuel coming in, and then it will generate more steam, and it will keep going, okay? So, but what we are replacing this with is solar, let's say solar panels, and they work with inverters, so they have to convert the DC electricity into AC electricity using the inverter. So there are no rotating parts. It converts light directly into energy. No stored kinetic energy whatsoever. The inertia constant of a solar panel is 0. No inertia constant, right? So there is nothing to arrest the frequency fall. So, okay, what we're going to, solar builds at a scale, coal runs less. So when we increase our solar, and then we even if we don't retire the plant, we'll have to back off, reduce the output of the coal-fired generator, or we can think about retiring it. And each megawatt we retire or reduce the output of the coal removes its H constant, inertia of the system. Therefore, the system inertia falls, and for example, it can go from 5 seconds to 3 seconds to 2 seconds to 1 second, which means that it will be able to keep the frequency going for 1 second, which is not long enough for system to recover, unless there is some fast-acting batteries and synchronous condensers in the system. Okay, same fault, deeper nadir is for smaller systems. So you've got the size of the system is also important. Now, why solar is important? Because as we saw, solar has got 200 plus gigawatts of potential in Indonesia. So it's going to be the big component of the renewable energy transmission. It's cheap. Also, it's easy to install, and it's cheap. So solar is going to be coming at a faster scale. So the frequency after the first 10 seconds after fault, frequency falls too fast to stop. With a low inertia, generator trip causes rate of change of frequency of 2 to 5 hertz per second instead of the typical 0.5 hertz. Under frequency protection relays, trip before governors can even begin to respond, removing more inertia and are accelerating the cascade. So the frequency fall, because you lost the generator, falls, and then you lose another generator because the frequency protection operates. You lose another generator. That means even less in the system, less inertia. So frequency trip of the remaining generators will work. They'll come out. So the generators are trying to protect themselves from fall of frequency. So once they sense a steep drop, they'll just come out. They'll come out, which will make the problem worse. Okay, so that's one problem. Another one, which requires 15 to 90 minutes around sunset. When the sun sets, solar output falls steeply. So if you've got a lot of solar generators in the system. When at the evening peak, there is no solar, right? So what you have to do is increase the output of your existing coal-fired or gas-fired generators. But generators cannot go from 0 to maximum instantly. So they have to, like cars, they have to accelerate, which is called the ramping rate of a generator. So many, they can only, I don't know, say it's a 200 megawatt generator, right? It can only increase its output by 2 megawatts per hour, right? So they have to know in advance and start increasing their output. So they cannot increase their outputs quickly. So what the system operator will do is not just give instructions to one generator to increase, it will give instructions to several generators to increase. So they will each contribute a little bit, but it will come, the total will be what is needed, but at a shorter time. Okay. So here the figure I have is net load on Java Bali can ramp at 3 to 5 gigawatts per hour. Okay, 3 to 5 gigawatts per hour. So if you've got solar which is greater than 5 gigawatts, right? You need 1 hour advance. You need to know 1 hour in advance to start increasing the output of your generators, because 1 hour later you'll lose the solar input. Okay, so you need to start increasing your generators. Remaining synchronous, so I think the Java Bali, from what I've found out, is between 4 o'clock and 8 o'clock window. Is ramping between 3 to 5 gigawatts per hour. And remaining synchronous plant must follow at maximum governor ramp rate. Any shortfall becomes a sustained frequency deviation. So if you can't match the load with your generation, the frequency will go down. So this is a 15 to 90 minutes around sunset. There's got to be some good dispatching going on. And midday, solar peak on low demand days. That means you're going to have too much power with solar dominated system. Too much power means over frequency. At solar noon, with low weekday demand, solar can exceed total load. Thermal plant cannot reduce its output fast. So they cannot increase their output instantly and also decrease. So they've got to ramp up and ramp down, right? So it's not like a light switch, put on, put off, right? So it's got to increase and it's got to decrease, and they've got a rate. It's like a car, acceleration and deceleration. It cannot be done instantly. So if you go over the frequency, again, the frequency protection relays will operate and will take the generator out, which will create further generation trips. Okay, so what can we do to stop this inertia, low inertia happening? Right? So bridging, so we have got bridging, transition and frontier technologies available. Right, so we've got a wide spectrum of technologies available. So bridging, transition and frontier technologies. So the bridge is clean coal, ultra supercritical coal-fired generation. So these are set to reduce emissions by 20 to 30%, because one of the reasons we are retiring coal plants is that, to meet our emission targets. Now, existing fleet can be retrofitted, or you can have new build coal-fired generators. And the advantage of this is that it preserves the system inertia. And there is a sovereignty dimension. It allows Indonesia to use domestic coal resources with lower emissions and giving it time for renewables to scale up. Okay. limit. What is the disadvantage? The disadvantage that it still emits carbon dioxide, and it's got long asset life, creates a lock-in risk, and so it shouldn't be a destination but a transition step. So new coal build is not totally out of the question because we have to manage the system inertia, right? But so a clean coal, ultra supercritical coal technology is possible, and the reason for it could be that you want to preserve the system inertia. And the danger is, once you build it, you've got to operate it for 30, 40 years before you can retire it. But it will reduce your carbon dioxide emissions, and it will give you time to replace it with renewable energy. So that's one option. So another bridge transition is carbon capture and storage. Now this kind of, you are still going to use coal, and you're still going to use gas. It will capture 85 to 95% of carbon dioxide, but it requires storage technology. There's a sovereignty argument, potentially extends the coal fleet life. Without climate penalty, Indonesia has got geological storage potential to store this capture and storage. And the downside, the negative side, is it's a high cost technology. There's a high energy penalty because 20% of the output of such generators go into this process of capturing and storage. So you don't get the full energy from that. Not yet, and also it's a new technology and it's not fully proven yet. Okay, so there are two bridging transitions which will allow you to use coal or gas, but they are not the end point. They are just like bridging, technologies. There is a transition frontier which I personally favor, and it is green hydrogen. And by green hydrogen I mean using geothermal and hydroelectricity to generate hydrogen. Right? And hydrogen can be generated, and there's a sovereignty argument for it. Indonesia can export green hydrogen and generate export revenue, and the money earned through that can be then introduced into the renewable energy sector and inverter technology. So the negative side is high cost today, and there are efficiency losses in conversion, and you need infrastructure investment. And our next frontier technology is small modular reactors. Factory built nuclear units, 50 to 30 megawatts, high inertia, zero carbon base load, and suitable for archaeopelagic deployment. Right? They could provide inertia-rich base load for isolated grids. Sovereignty requires domestic fuel and expertise. And the limit is not yet commercially demonstrated. 2030 is the earliest realistic deployment. And of course, you need the regulatory frameworks for this. Now, I mentioned this because in connection with data centers. Data centers are coming in as big load consumption centers. And you can't refuse to have them because that will hinder your development. But when they come in, you've got to provide this load. But data centers know that where they are being hosted, they create huge demand problems for the hosting country. So they are trying to develop this technology so that the data centers will be using these small modular reactors, so they will not suck energy away from PLN, and they will operate as an independent mini grid with connections to the PLN grid for backup. Okay, so this technology, this is the opportunity for Indonesia to go in and become a joint technology provider. Ask data centers, you can come in, use this technology, but Indonesia has to be a technology partner. transfer the knowledge, and you got wide range of university background, and you'll have physics departments, nuclear physics departments, and you provide a skilled workforce, manufacturing facilities, and this could be a good opportunity. Right, so coal provides 60% of Indonesia's electricity today, and they provide the synchronous inertia that the current grid currently depends on. If you retire coal too fast, inertia cliff before renewables are ready and in the system. If you retire coal too slowly, stranded assets, climate commitments missed. Indonesia has got 100 gigawatts of relatively young coal plants, average age under 15 years. Most coal plant operates 25 to 30 years. There are power purchase agreements with PLN. An early exit will trigger financial penalties. It could be on average £1 million per plant. So you have to decide, how fast you go along this road, because Indonesia did not cause the climate change, so it's got right to develop its industry and increase its living standards. Sequencing decisions belong to Indonesia, not to external creditors or climate agreements alone. Sovereignty deployment policy transition at a pace. For coal communities, also a domestic equity obligation, not a Western demand. Green financing terms that respect sovereignty are fundamentally different from conditional agreements. Now, there is a 20 billion commitment by the Joint Energy Equitable Transition, and bilateral managed phase-down programs offer financing paths, but terms must be negotiated really well, right? So you have to develop your own path through this, and try and negotiate equitable solutions for Indonesia. Engineers, this is what I've been saying, engineers cannot hide beyond policy. They must provide honest sequencing analysis. Which plant retires first, which island, what renewable capacity must be in place before each coal plant retirement. Clean coal synchronous condensers, carbon captures and storage are all possible technologies, and engineers will have to calculate what buys time for you to make the transition and at what cost. Every coal retirement decision is also a stability envelope decision. Engineers' job is to make sequencing technically achievable, and tell the decision makers exactly what the cost of each option should be. Right. How much time have I got left? 30 minutes. Okay. Okay, so you mentioned this briefly, but 97% electrification rate in the country, but outer islands reliability is far lower than Java, Bali. A third of Indonesia's population are in areas where power cuts remain common, and the elephant in the room is the subsidies. So there is an effective tariff gap between subsidized rate and cost of supply in remote area. PLN absorbs the difference, but PLN absorbs the difference means the government absorbs the difference, right? So this is obviously not a sustainable path. So there must be a way through this. Coal phase out must not raise tariffs for rural and outer island consumers. Survivability standard exists so that the last mile never loses power during the frequency event. Now, we have to have survivable standards and survivable grids, because if a grid that fails the frequency test fails, the communities that can least afford it lose power to the to access to electricity. So data centers are the new load coming onto the system. They have no tolerance for outage. Their scale is huge. Their scales are huge, between 100 to 500 megawatts. And their demand could double by 2030. And Indonesia is attracting investment because of its location, very strategically located. Another elephant in the room is privatization. Right? So privatization means independent power purchase, entering market that may prioritize dispatch economics over grid stability, because all they are interested is selling their energy. So the problem is already complex, but privatization puts another layer of complexity on it. There's a inertia provision is a public good as far as private producers are concerned, and it doesn't have a private revenue stream. So if they are going to sell megawatts, they are only interested in selling megawatts, right? Whether that megawatts they generate is through solar or wind. Solar and wind means reducing the system inertia, but there's no obligation on them. So an obligation, there must be a way during privatization to put the obligation on them also to provide inertia to the system. IPPs live with power purchase agreement revenues, and they have no voluntary incentive to retire early. Only regulatory or financial instruments can create that incentive. Right? So if you're a coal plant owner today, why should you retire? You've sold your energy for 25 years, right? So there's no reason for you to retire unless there's a regulatory obligation or a financial incentive for you to do this. Managed coal phase down via power purchase agreement renegotiation requires PLN to retain sequencing authority even as the market opens to private operators. So even at high level you decide, we have to retire coal plant, but the decision, the final technical decision must belong to PLN because they are the ones who are operating the system. So they have to make sure they are operating in a safe operation zone. Coordination between private operators and PLN system control is a must and must be developed to a great sophistication. Okay, so last column there, 6% demand growth in 2024. Data centers concentrating load in specific corridors, industrial electrification and electric vehicle fleet emerging simultaneously. So as Indonesia develops, the industrial load is increasing, electric vehicle electrification is increasing. So the geographical positioning of the load is changing as well. Peak load profiles shifting, less predictable than residential growth. Because you can forecast residential growth. You can say so many kilowatts per person, so many houses. It's easy to forecast. But changing industrial composition and electric fleet, it makes that forecasting even more difficult. Okay, so when you retire coal, you have to also retire coal plant where the new load is not emerging, right? So they are the last coal plants to retire. So coal retirement sequencing must now account for new load centers as well. As IPPs enter the market and data centers scale, who holds the inertia obligation is a question that you must answer. How does the regulatory framework assign grid stability as a responsibility when generation is no longer a public monopoly? Okay. So these are important questions and open problems that your generation needs to answer. Okay, so this is more details on what we says. No, you can't see it. I can see it. There you go. Right. Okay. So we've briefly touched on this, and there are more details that you can study this in privately, because I've made lecture notes to be given to you. Right. So contract lock-ins, data center load growth, privatization of generation, demand growth, and rephasing, based on rephasing the generation that should come in and the generation that should come out, has to be in parallel with the demand growth. So coming back to reliability, resilience, and survivability, systems perform as designated under expected conditions. That's a reliable system. And the tools you use are N-1, N-2 criteria, reserve margins, planned maintenance. Resilient system can absorb disturbances and recover on even unexpected ones. Tools that you use: redundancy, fast restoration, demand flexibility, and self-healing networks. And that form of operation assumes that recovery is possible and the system bounces back within short time scales. Survivable systems means that it's a system which remains stable through compound cascading extreme events. Right? Compound cascading and extreme events means more than one event. For example, lightning strike and landslide and heavy rainfall. Right? So they are all adding to the effect of the other event. And cascading means one part of the system fails and it causes another part of the system to fail, like cards falling on each other. So that's a cascading event. And extreme events are like the events, the cyclone we Indonesia's experience, say in Sumatra, for example. It's an extreme event. It's not a normal expectation. But the systems that you design must be able to cater for all these different contingencies. So the tools you need for that is dynamic envelope management. Envelope, this is by envelope I mean the operating zone. Envelope monitoring, synthetic inertia, and artificial intelligence assisted control. So these tools mostly do not exist at the moment, and some of them are in research phase, being developed at universities, and most of it is what you have to do, so and work at. Target design, standard for renewable dominated high inverter based resource systems, is the target for developing all the tools mentioned in the survivability role. So back to the inertia. So what do you think the answer to the question is? Your grid has 2 seconds to respond. What happens when it's got 0.4 seconds? Right. Okay, so I will try and answer this. As I said, rotating machines store kinetic energy in their spinning mass, and sudden changes in energy resist changes in rotational speed. When generation trips, inertia slows down the frequency fall. So it buys time for the governors to react and respond, and this time is measured by inertia constant, which is in energy stored over rated power. And typical values, if you remember, of H, which is the inertia constant, is for thermal systems is 3 to 6 seconds. Hydro systems is 2 to 4 seconds, and the solar and wind has got zero inertia. So so when we are retiring coal and we are increasing wind and solar energy, the system inertia gets lighter every year. So we have to find ways of replacing it. So this is the equation. I don't know if you've studied this, but you probably have. This is how you calculate the change of power, or you can calculate the inertia constant of the system. But what you should take away from this equation is that as the h, which is the inertial constant, falls, df dt rises for the same change in power. So there's an inverse relationship. Half the inertia causes twice the rate of change of frequency. Right? So the cascading blackout happens step by step as such. Now a fault happens in the system, a generator trips or a large load disconnects suddenly. Power balance that we've been talking about is broken. System has got microseconds before frequency changes become destructive. So what happens in coal-dominated systems, high inertia systems, is the kinetic energy arrests the frequency fall. Synchronous machines give up their kinetic stored energy to maintain frequency. Larger the system, H, the more energy available, the slower the fall. With low inertia systems, rate of change of frequency exceeds threshold. With little kinetic energy in the system, frequency falls sharply. A rate of change of frequency exceeds 1 Hz per second. Therefore, the protection of the generators under frequency relays operate. They take the generators out, which leads to further change delta P, and so the frequency keeps falling. Because the protection relays now trip all generators before the generators can respond. This reduces the total inertia even further. So it's like a chain reaction, such chain reaction accelerates the cascade, and it doesn't stop it. And then you go below 47.5, which means all generators start tripping out, and then that's where the blackout happens. So green line is the green line is high inertia systems. They can recover loss of power. Low inertia systems drop suddenly, and they can't below 47.5, and they can't recover. So that situation leads to cascading events, which can result in blackouts. Now that is why in the new system we've got to be very careful how we set the relays, and maybe have seasonal settings, because the relays can conflict. The rate of frequency change setting for embedded generation is 0.5 Hz per second. Trip if exceeded for time duration longer than 500 milliseconds. And then there is 1 Hz per second typical distribution connected generator trip settings, and that triggers before governors react, and 2 Hz per second trips transmission connected threshold in some areas, still trips before the system recovers. Now when rate of change of frequency exceeds the relay settings, the generator trips, removing inertia from the system, accelerating the cascade. Now what is the solution for this in the future? So adaptive protection is one way forward. Widen the relay deadband, so the trip settings, adaptive rate of change of frequency protection, relays that read the system inertia in real time and adjust thresholds. Now these are becoming available, technologically possible, new protection systems. And then also another technology is virtual inertia forming inverters. These are also new technology, but are being implemented now. Grid forming inverters, they emulate inertia, reducing the rate of change of frequency before any relay threshold is reached, and that removes the trigger. And inertia monitoring plus SCADA integration. Control room gets real-time inertia warning when system approaches vulnerability. Operators can then reduce demand or dispatch, reduce the renewable dispatch and remove the low inertia generators from the system before such events. So there are possibilities and new technologies are coming in. So we've talked about this before, so I'll just go forward. So what you want to do is operate in this system, green system. Right. So the green zone is more like the Java Bali, and the red zone is more like Eastern Islands, and the orange zone is the inflection point where system can easily trip into the red zone and lose frequency so fast that you cannot recover. So you want to. So this is a graph which shows you the inertia constant in the y-axis, and on the x-axis you have the renewable penetration, right? So you can see that even with low renewable penetration, Eastern Islands are in the red zone. It's because the percentage of the inverter-based resource is high, so it's a low inertia system. So they are continuously kind of between orange and red zone. Whereas you want to, as the renewable penetration increases to about 60%, Java Bali will still be in the safe zone, right? So, and that's where you have the 60% coal reduction anyway. So that maybe I'll also talk about the bridge. People talk about safe capacity margins as you introduce renewable energy. So how much extra capacity you should have in the system as reserve when you introduce renewable energy into the system. So at the moment people are talking about, for present system, UK operates with 30% reserve margin. So they've got in 30% more capacity, installed capacity than their peak load. So that, but when you approach 60% renewable energy, you should have installed capacity should be about 50% more than your peak load, right? So you should have more 50% more installed capacity than your peak load for high renewable energy dominant systems. So that's the new planning criteria. So, okay, today is 5.5 seconds for Java Bali, 10% IBR renewable energy. The trajectory for 2030 is 40 to 60% renewable energy, and then the inertia constant will come down to between 2 and 3. So that Java Bali in 2030 will be in kind of a stress zone. Must deploy synchronous condensers and grid forming inverters now before penetration climbs to stress zone. And the window for doing that is 5 to 8 years. So within 5 to 8 years, those will have to be done. Largest system but because of the percentage of coal generation in the system, most inertia to lose. Highest consequence of failure because it's an industrial and dense urban centers. Priority is phased inertia management plan, phased withdrawal of coal. Sumatra, Kalimantan today is between 3 and 4 seconds, 15 to 25% IBR resources. It's marginally safe zone, but by 2028 and 2032, which is not a long time away, the inertia constant can fall down to about 2 seconds, and the expected IBR is minimum 4T according to the forecast. It could be 60%, and it is going to be a stressed operational zone. The risk of cascading failures. Action required already in early distress zone in some system states. Fast acting, fast frequency recovery battery deployment is urgent. The system needs synchronous condenser retrofit for retiring coal plants. So retiring coal plants will not generate electricity, but they'll be on spinning reserve. So they'll operate to provide the inertia. Transitional systems face the inflection point earliest. Some are operating near the ridge on peak solar days. Eastern Islands today 1 to 2 second inertia, about 20 to 45% renewable energy resources, and they are operating at the moment and for the next 4 or 5 years beyond safe limits, so there are frequent breakdowns and blackouts. What they need fast is grid forming inverters, demand flexibility, islanding detection, and so that is the urgent case for Eastern Islands. Have I got 10 minutes or 15? No, 10? Right. Okay, I think I'll finish. Okay, the standard model will give you adequacy installed based on installed capacity and reserve margin, and the change of operating point is linear, and more capacity means more adequacy, so that's the way system operates. Does not model inertia or short circuit ratios, and it is designed for synchronous dominated systems, which Java Bali is at the moment. So the question you are trying to answer by your analysis is, do we have enough capacity? Now, the future operating models is a dynamic envelope model, and the adequacy is boundary within three-dimensional operating space. It is non-linear, and it will model penetration of renewable energy, one dimension, inertia another dimension, and reserve is another dimension. And the planning and analysis, operating analysis, will have to be done according to these three dimensions. And the question that you are trying to, what you are trying to find an answer to is, where is our operating point relative to the stability boundary? The operators need to see system inertia updated every scan cycle for current IBR penetration, so they have to see what IBRs they have in the system for the next 2 hours. That means solar forecast. Minimum, sorry. Okay, this is what the operators need to see, right, for high renewable dominated systems. Real system inertia, updated every scan cycle, current IBR penetration, solar forecast, minimum synchronous generation online, or head dispatch and dispatch headroom, distance to inertia inflection, threshold, like a traffic light indicator, like the graph I showed before. There's the green zone, orange zone, and the red zone. Rate of change of frequency headroom before any rate of change of frequency protection relay strip. So this is what the operators in a renewable energy dominated system needs to see. And the decisions they need to make is when to commit the synchronous condensers or mothball synchronous plant, when to curtail IBR output, maintain the minimum inertia constant, and demand flexibility action, called industrial loads to modulate, islanding decisions, should the system run alone or seek for interconnection, pre-positioning the fast frequency response battery reserves before the solar peak. Of course, in Indonesia you've got pumped storage, so they need to schedule the pumped storage as well. Now what the tools they need and is being researched at the moment is envelope dashboards, phasor measurement units fed real-time inertia constant estimation. And there are some operational, UK has some of this in their dispatch centers. Inertia forecasting, combining unit commitment with solar and wind forecast, and develop digital twins where they can do this live simulations in advance of the real time, and autonomous envelope monitoring with operator alert thresholds, and then artificial intelligence assisted inertia scheduling, optimization. This is also research stage, your work. So, the last column there is what needs to be developed and exists, maybe a bit of it, but not all of it, all the system. So this is what the universities are working on, and research is being developed on these. And this is the middle section, is what the decisions you are going to face when you are working as engineers. So technology is available, and some of them are new: grid forming inverters, fast frequency response batteries, synchronous condensers, phasor measurement units. So you should have good knowledge of these before you graduate. Okay. Commercially available now, grid forming inverters, but they have not been employed at a large scale, right? So they are. When you are working in your working lifetime, they will be being employed at a large scale, and there's a coordination. There's going to be a coordination challenge there. Fast frequency response batteries, they respond within 1 to 2 seconds of contingency. Now remember, the low inertia systems, inertia is like 1 to 2 seconds, so these are good. So they can come into play with low inertia systems. Synchronous they will fill the critical sub-second window at low inertia, and they're being used in Australia, Ireland, and UK. So they are proven technology which you need to operate during your careers. Synchronous condensers are the best option for weak systems where inertia is critically low. They provide true physical inertia and reactive power without consuming fuel. Mature technology, but it's underutilized, and it's underutilized because there is no need for it, not much need for it until today, and will be more need for it in the future. Phasor measurement units, they measure real-time measurement of voltage, current, and frequency across different points in the network, and makes the envelope operating zone visible. And they are deployable now. It's an existing technology, critical, and so critical enabler for all other interventions that we talked about, that the that the operator needs to see and to help with the decisions they have to make. Okay, so more of this will demand flexible. I've talked about geothermal steam turbines, pumped storage hydro. These are two-level reservoirs. When there is excess energy, you pump the water up, and then when you need the energy, you let the water come down through the turbine to generate electricity. So they are like big batteries, kinetic energy batteries, right? You pump the water up when you have excess energy, and then you pump the water down, you let the water come down to operate the turbine. So there are good technologies to have for storing the energy, also helping with the frequency. So their age is between 4 to 8, which is good. And you can also have geothermal steam turbines, because they are steam turbines and they've got good inertia constant. So you can put these in operation before retiring the coal plant so that the system inertia doesn't fall suddenly. Last actor in the scene is demand flexibility, which is controllable loads. And this has got to be more and more of this, so that these are loads which are change their consumption. And then if the system dispatch can ask them to reduce their load when there is not enough generation, they can reduce their load. That will keep the system stable and balanced. So, or if the one big generator is lost, you can ask them to reduce their output or consumption. So demand flexibility is controllable loads for industrial. This is appropriate for industrial data centers, industrial loads, electric vehicle charging, cold storage. They can modulate or change their consumption within seconds of a frequency event. And although they don't add inertia directly, but they reduce the delta P disturbance, shrinking the required inertia for any given frequency fall. So I've titled this here, the roadmap. Sequencing matters as much as selection. Sequencing is, well, right. So this is the roadmap, right? So stabilize the baseline. Stabilize the baseline, prevent H from falling any further. And the second phase is to build inertia back in through synchronous renewables. And phase 3 will be transition to high IBR operation envelope managed grid, right? And these are roughly the time scales. Now, maybe 2 or 3 years, and then phase 2 is maybe it's got another 5 to 10 years, and phase 3 should be completed by 2040, because that's the renewable energy target set by the government. And and these are the things that you could. The second column will have the things that can be done. At the moment, phasing measurement units roll out, have more of these in the system to increase the inertial constant visibility across all different, the strong networks, the transition networks, and the eastern islands. Install more frequency response batteries. Install more grid forming inverters at the mini grids in the outer islands. And then maybe have a regulation which says all new solar above 50 megawatts should include a grid forming capacity or capability. Start synchronous condenser retrofits. Start experimenting with demand flexibility and renegotiate power purchase agreements. Phase 2, increase installation of geothermal plant installation, increase pump storage capability, scale up demand flexibility, start implementing adaptive rate of change of frequency protection rollout, replace all static relays across all transmission, start researching into digital twins, especially for Java Bali grid, and work on detailed managed phase down. First tranche of early call retirements will be funded through bilateral agreements with international funding. And for the future, longer term, inverter dominant, we are getting to the inverter dominant network. All new renewable energy must come with grid forming inverters. And then by that time develop real-time envelope management, maybe study inter-island connections for the eastern island, introduce more geothermal, and also look into the possibility of green hydrogen. So this is the developing and to be developed, which I've talked about this, so I'm running out of time, so I'll go forward. So the engineer and the power system is being redesigned. The interface has to be redesigned, and this will what the power system engineers will be working for in the future. Real-time system inertia dashboard, envelope forecast, AI-assisted inertia scheduler, digital twin integration, demand flexibility portal, and island autonomy monitor. So this is my forecast for what we'll be using in the future. So this is a good time to stop, because I think we've got some time for questions.
Okay, thank you so much for the explanation. Now we'll move to the Q&A session. Any question from the audience? Okay, maybe from Zoom, you can raise hand or using chat feature. Okay. Well, maybe the first question come from me.
Okay.
Yeah. Why PMU is necessary in the IBR dense power system? PMU.
Yeah, because this will give you real-time information on voltage and frequency, and that will help you to determine also because you'll also know the inertia of the system. That will help you to decide whether you are in a safe operating zone or not. So you can load shed, bring in new generation, or load shed to keep the age in the safe operating zone. Or another thing you can do is you can have seasonal setting of your protection relays. So at the moment it's just set once for the year, but you can then change the setting. But because there are so many relays, you have to find an automatic way of doing this. Right?
Okay, thank you. Maybe one more question from the audience. Okay, thank you. Bye-bye.
Dr. Suhail, it's an honor for us, all of us, to hear your experience and your presentation. I just would like to know what is your opinion about the conversion of the, as mentioned on the asset there, PLN asset on the stranded asset there, on the coal-fired power plant. So, how is the possibility, from your experience and your view, how to have a conversion program from the coal-fired plant into the biomass power plant, 100% conversion program?
Well, um, these are the questions. Well, you have 60% Java Bali, 60% coal, right? And then outer islands on diesel generators and some solar, and you have to put more solar in because there's a problem of 700 different networks. Most of them are in the outer islands. How to get the diesel fuel to them, right? So way forward is introduce more geothermal, increase your hydro capability, increase your biofuel generator, because these are all inertia preserving technologies, right? And then once you have them in place, you can start retiring the coal plants. You'll never be able to retire all of it. So I think there will be maybe 20-25% left, at least, of coal plants. But the remaining coal plants will have to be the clean technology and carbon storage and capturing technology coal plants. And the transition to this, in my previous slides, will be increase your monitoring capability so you can keep the system balanced, because you'll have a lower and lower inertia constant. So you have to increase your control and observational capability so you can keep it. So when the system inertia falls, you can just drop load or put more synchronous connectors in. You have to manage your dispatch. So it is a very complex problem, but it can be done. And it's a matter of having enough finance to do this. So technically it is possible to sequence and phase it. But whether you will have enough financial resources to do this, because to come out of it early needs money. Because you have to pay the power purchase agreement. Right? To introduce new technology also needs funds. Right? So you have to optimize. I don't know how much the Indonesian government can or spend on this. Right? There's subsidy problem as well. There's subsidy. You have to find finance for renewable energy. You've got to find finance to draw them out, or just to leave them to run until their end of their lifetime. But when you get new coal in, only have clean technology and with carbon capture and storage facilitation. All you need is to buy time now, right? You need to buy time to find finance and for the new technologies to develop. And you can do it by going hydro, going geothermal, going biofuel. But that also needs money. So, and these are infrastructure projects, because from concept to implementation, probably at least 10 years. When I think of the idea, do the analysis, make the plan, go and get environmental protection permissions and find the money. From conception to implementation, I think the shortest one is just going to be like 8 to 10 years. So, and then meanwhile your load will keep growing. So you need to be very fast-thinking engineers and fast researching the problems. And these are the questions you need to answer all the time. I'm afraid I don't have any easy solutions for you, or answers, but so they are good challenges to have. You are going to be in interesting times. I don't know, that is maybe a Chinese curse, but may you live in interesting times, which we are living in interesting times. Yeah. Yeah? Yes? Yes? Yes, of course, yes. Yeah. Yes, of course. Yeah. Yes. Yeah. I'll be happy to contribute. As you say, Warson has long experience of dispatch centers, and his research was on dispatch, wasn't it? On neural network dispatch. Yeah. So, and that was a long time ago. So it was really forward-looking dispatch, genetic algorithms and neural networks. So yeah, I mean, you need these new tools because the challenge is huge, the problem is complex, and there are like elephants in the room as well, which we haven't even started thinking, like privatization, data centers, demand flexibility options. So there's huge challenges coming. I hope I was able to, I mean, because it's a very, very long period to talk about it. So I was trying to include everything. And sometimes I went too fast, but, I need like a full day really to go at a comfortable pace. This is why I've prepared lecture notes. So I'm happy for you to distribute it to the participants, and you can put it on the online. Yes, I'm also happy to contribute to future discussions or research ideas or research supervision. I can do it over the internet, so it won't be a problem. Yeah. Yeah. I mean, when I was getting trained as an engineer, we only concentrated on the engineering side. So because, I mean, I graduated in 76, right? So it was just like do the calculation. We need energy, build as much as possible, as soon as possible. That was the first criteria. And then when I graduated, I started working as an engineer. I realized I didn't know enough management. I didn't know anything about finance and whatever, right? So when I started teaching, I decided to introduce management and project management and finance into the engineering education. Because as an engineer, you have to do these things without any formal training. So I ran a master's degree for about 25 years, which had strong management input to it. And then now I'm thinking, now you have to go one step forward. You have to know a lot of a good programming language, and you also have to have very good communication skills, because you need to explain things to people who don't understand technology. Right? Before we didn't worry about these things, just did it. You have to accept it. But now the problem is more complicated. You've got to understand about privatization and policy making, regulation. You've got to understand economic rules about privatization. So engineering is becoming more and more complex these days. And there is this knowledge half-time as well, which I mentioned. So you need to keep updating yourself. But makes life interesting. Otherwise life is boring. Thank you.
Okay. Thank you so much, Dr. Suhail, for the presentation. Please give a big applause for Dr. Suhail. So, to close our session, MC.
Well, thank you very much for coming to listen to me and spending time. I hope it's been useful, and look forward to many more collaborations.
Okay, thank you very much, Dr. Suhail, and thank you, Mrs. Hasna, for being our moderator today. And as a symbol of our deepest appreciation, we would like to present a token of gratitude to Dr. Suhail Osveran. So you may stay in the stage, and I will invite our Dean of Faculty of Electricity and Renewable Energy, Ibu Dr. Rumi Sirait, to come to the stage. And Mrs. Hasna, also, you have to go to the stage, please, to take a photo with Dr. Suhail and Ms. Rumi. Please give a big round of applause for Dr. Suhail. Thank you very much for sharing with us today. Okay, thank you very much, Mrs. Hasna, Ibu Dr. Rumi, and Dr. Suhail. You may have a seat. Okay, distinguished guests, lecturers, and students, what an inspiring and impactful session we had today. Dr. Suhail, you may have a seat. Thank you very much. And now, before we come to an end, I will invite all distinguished guests for take a group photo session with Dr. Suhail. Please, documentation. Maybe we all come to the stage, please. Foto. Muat nggak? Cukup. Oh, dari depan aja. Okay. You may have a seat so we can take a photo from the stage. Mas Rahmat sama Mas Ilu ambil dari depan aja. Oh, Fasya, oke. Iya kan, nggak enak. Oh iya kan. Oke. To all participants, please. Okay. Sorry, I will. To all participants, please go to the stage. We will have a photo session with Dr. Suhail. Please take your place. Ayo. Mari Bapak dan Ibu. Ya kok Bapak? Okay, ready? Oh, naik. Okay, I will count. So 3, 2, 1, cheers. Once again. Thank you very much for all the participants. You may have a seat. And on behalf of Institute Technology PLN, we extend our sincere gratitude to our speaker, university leaders, PLN representative, committee members, and all participants. Let us continue building global collaboration, advancing innovation, and empowering future energy leaders. I am Septianisa, your MC today. Thank you and have a productive day ahead. Assalamualaikum warahmatullahi wabarakatuh.
Yes,